So, um, picture this. You are sitting on an airplane, right? Just parked on the runway.
Oh, yeah, we've all been there.
Right. And the engines roar to life, the brakes release, and as the plane rockets down the tarmac, you feel this like massive, invisible hand push you violently backward into your seat. We have all felt that exact sensation.
Oh, absolutely.
It is visceral, it is undeniable, and well, according to the laws of physics, it is a complete illusion. You are not actually being pushed backward at all.
Yeah, your brain is it's desperately trying to make sense of the sudden pressure on your chest. So it
Yeah.
creates this narrative, right? It says, something must be pushing me back.
But that's not what's happening.
No, the reality is a forward collision. Your body is simply trying to hover exactly where it was over that specific patch of runway. It's just obeying the universe's ultimate law of cosmic laziness, honestly.
Cosmic laziness, I like that.
Yeah, and the airplane seat is just violently accelerating forward and crashing into you.
That is just wild to think about. Welcome to today's deep dive, everyone. We are um, stripping away the illusions of everyday movement to reveal the hidden mechanics underneath.
Gonna be a fun one.
It really is. We're working through this incredible stack of presentation slides titled The Invisible Rules of Motion. And since you, the listener, probably already know the basics of high school physics, you know F equals ma, you know what a Newton is, our mission today isn't to just rehash textbook definitions.
Right, nobody wants a boring lecture.
Exactly. You
Yeah.
really want to simplify these fundamental physics concepts for students or just anyone who wants to see the hidden mechanics of everyday reality. We are taking these formulas and exposing how they actually dictate every single physical interaction you have.
From the car you drive right down to the joints in your knees. Because when you stop looking at physics as just, abstract variables on a chalkboard and start seeing it as the structural blueprint of reality, it changes everything.
It really does.
You start to realize that stillness and movement are not passive states. They are the results of this massive, complicated web of pushes and pulls that are constantly fighting each other in three-dimensional space.
Okay, so let's unpack this. To map out that blueprint, we really need to set a baseline and talk about those invisible pushes and pulls, which we call forces.
Right.
And just a quick refresher. The universal unit is 1 Newton, which is simply 1 kilogram multiplied by meters per second squared. But the most critical thing to grasp about a force is that it is a vector quantity.
Yes, vector is the key word there.
Right, meaning the sheer magnitude, like how many newtons of muscle you put into a push, is completely meaningless if you don't precisely account for the direction.
Direction is literally everything. I mean, if you apply a massive force to an object, but your vector is just slightly off the center of mass, you don't get linear movement. You induce rotation, torque, instability.
So you just spin it instead of pushing it.
Yeah, exactly. This is the foundation of dynamics. To navigate three-dimensional space, the universe operates on a very strict set of rules governing these vectors.
Which brings us back to that airplane seat, right?
Oh, yeah.
And the universe's stubbornness. We're looking at Newton's first law here, inertia. It tells us that an object wants to keep doing exactly what it's already doing forever, unless an outside force intervenes.
And what's fascinating here is how inertia scales with mass. Because inertia isn't just a concept, it is a physical resistance to change. The more mass you have, the more the universe insists you, well, stay put or keep moving.
Right, so that airplane seat hitting your back is the external force trying to negotiate a change in your state of rest.
Exactly. And the heavier you are, the harder that seat has to crash into you to get you moving at the same speed as the plane.
So if inertia is the baseline, how do we actually force a change, mathematically?
Uh-huh.
The second law quantifies this with net external force.
Yeah.
F net equals mass times acceleration.
A classic equation.
But I want to push back on something in the source material here.
Okay, let's hear it.
The slides make this absolute distinction between internal and external forces. They say internal molecular forces pushing and pulling on each other don't count toward moving an object. So, and I know students get tripped up on this, if I am swimming in a pool, I am using my own internal muscles to pull my own arm. How is that not an internal force moving me forward?
Oh, that is a brilliant point of confusion. And it all comes down to where you draw the boundary of your system.
The system.
Yeah. If the system is strictly defined as just your body floating in a vacuum, your muscles contracting are internal forces. They will never alter your center of mass. You could flail your arms forever in outer space and you wouldn't travel an inch. Your F net just remains zero.
Wait, really? But I'm not in a vacuum. I'm in water.
Precisely. You are utilizing the water. When your hand pulls back, you are applying a force to an external object, the water, and then the water applies a force back on you. That is the external force that actually propels your body forward.
Oh, wow. So this is why if my car breaks down, I can't just like sit in the driver's seat and aggressively shove the dashboard to make the car roll forward.
Exactly. Your hands pushing on the dash and the seat pushing back on your body, those perfectly cancel out within the boundary of the car. The F net is zero.
So you need an outside push?
You need an external system. You have to get out, stand on the road, push the ground backward with your feet, and push the bumper forward with your hands.
So you literally cannot move yourself. You can only negotiate with your environment and force it to move you.
That is the profound reality of the third law, the symmetry of action and reaction. It dictates that every movement is a partnership with the physical world. You push the ground backward, the ground pushes you forward.
Okay, so that covers how these vector pushes and pulls negotiate movement. But what does this all mean for when we aren't moving? Like, look at a coffee cup resting on a desk, or you and I just sitting here in these chairs. We are perfectly still, but we aren't free from force, are we?
Oh, not at all. We are actually in a state of violent, perfectly balanced tension.
Violent tension.
Yeah, this is vertical equilibrium. The sources illustrate this with a free body diagram of a block resting on a flat horizontal table. The block has weight, which importantly is not its mass.
Right, students mix those up a lot.
They really do. Weight is the local gravitational field aggressively pulling that mass downward toward the center of the Earth.
So gravity basically wants to pull the block right through the solid wood of the table.
But the table refuses to yield. It exerts what we call a normal force. That's a perpendicular force pushing straight up against the block.
And on a flat surface, that upward push perfectly matches the downward pull of gravity, right?
Exactly. The vectors cancel out to zero. The block sits still.
Now, the slides highlight something incredibly nuanced here about how gravity interacts with objects in this state. There's the center of mass, and then there's the center of gravity.
Ah, yes.
And I know these terms get thrown around interchangeably all the time, but they're fundamentally different concepts, right? I mean, center of mass is purely geometric. It only cares about how the physical stuff is distributed.
Yeah, it is the mathematical average position of the mass, completely independent of the universe around it.
And it doesn't even have to be located on the object itself. Like
Yep.
the center of mass of a donut is just floating in the empty air of the donut hole.
A perfect example. Geometrically, that empty space is the balance point. Now, center of gravity, on the other hand, depends on the mass distribution plus the surrounding gravitational field.
So what does this all mean? If they're fundamentally different mechanisms, why do we constantly treat them as the exact same thing in everyday student problems?
Because we live in a uniform gravitational field. On the surface of the Earth, gravity pulls on the top of your head with practically the exact same force as it pulls on your feet.
Okay, so they match up.
Right. The slides show a diagram of a bowling ball and a human body. Under uniform gravity, like our everyday life on Earth, the mathematical center of mass perfectly overlaps with the center of gravity.
But if we zoom out to the macro level or like look at extreme astrophysics,
That's exactly where the distinction becomes critical. Take an incredibly massive structure, or a satellite orbiting a planet. The gravitational pull on the side of the satellite closest to the planet is tangibly stronger than the pull on the far side.
so it's an uneven pull.
Yes, a non-uniform field. And that actually shifts the center of gravity away from the center of mass. The geometric center stays put, but the balance point of the gravitational pull moves closer to the planet.
Which introduces torque, because that uneven pull causes the object to start rotating just from gravity. That is just wild to think about.
It really is.
Okay, so vertical equilibrium keeps things from falling through the floor. But the moment we try to break horizontal equilibrium, say, we try to push that block across the table, we slam into an entirely new, deeply frustrating opposing force.
Friction, the universe's ultimate resistance mechanism.
Right. And friction is born from the physical contact between two surfaces, and its only purpose is to oppose motion. You push left,
Yeah.
friction pushes right. The slides use the example of a lawnmower. If you're pushing a lawnmower across the grass at a constant velocity, meaning zero acceleration, so F net is zero, you aren't overpowering friction. You are meticulously, perfectly matching its backward push.
Yeah, if you push a fraction harder, you accelerate. If you ease up, the friction vector takes over, and you just grind to a halt. You are constantly balancing that equation just to take a single step forward.
But friction isn't just one monolithic force, is it? The slides break it down mathematically into two distinct states. You've got static friction when an object is locked at rest, and kinetic friction when it is sliding.
Muss and muck.
Right. And the math reveals something we have all physically experienced when trying to move a heavy piece of furniture. Because the static coefficient muck is always greater than or equal to the kinetic coefficient muck, it always requires a larger force to overcome static inertia than to keep it sliding.
It takes significantly more force to break an object out of its static inertia. But if we dig into the why behind that math, it's all about microscopic geography.
Microscopic geography.
Yeah, no surface is perfectly smooth. At a microscopic level, your coffee cup and your desk look like jagged mountain ranges.
So when the cup just sits there, those microscopic peaks and valleys just kind of sink into each other. They interlock.
They literally form microscopic cold welds.
Hmm.
So, to initiate movement, to overcome that static friction, you have to apply enough lateral force to actually shear off those microscopic jagged peaks or lift the entire object up and over them. And that requires immense energy.
But once you break that lock and get it moving,
That's kinetic friction. The object is now just skipping rapidly across the tops of those microscopic peaks. The surfaces don't have time to sink in and interlock again, which is why the kinetic coefficient drops and it suddenly feels easier to push.
here's where it gets really interesting. The slides map out how different materials influence these coefficients, and the variance is just staggering. They list the grippers, like rubber on dry concrete. The static coefficient is 1.0, and the kinetic drops to 0.7.
Which is incredibly high resistance.
Right. Right. Which is exactly why cars can take a corner at 60 miles an hour without flying off the road.
You want maximum static interlocking between the tire and the asphalt.
But then you look at the standards, like wood on wood, which are around 0.5 and 0.3. And then the sliders. If you take perfectly smooth steel sliding on dry steel, it's 0.3. But if you add heavy lubrication oiled steel, the kinetic coefficient plummets to 0.03.
That is pretty much the absolute pinnacle of human mechanical engineering trying to eradicate resistance.
It's incredibly slick. But nature beats us. The slides introduce these biological marvels, human joints. Your bones, when lubricated by synovial fluid, achieve an ultra-low kinetic friction of just 0.015,
It's a near frictionless miracle, really.
half the resistance of highly engineered oiled steel. We walk around with these perfect mechanical sliders inside our knees and elbows every single day, completely taking for granted that human evolution engineered a better low-friction environment than a modern machine shop.
And that fluid operates under massive compressive loads without breaking down, which is something synthetic oils really struggle to do. It's a beautiful piece of context. Now, friction forces act strictly along the boundary of a surface.
Right.
But how does the universe transmit force across a distance through a material?
That's the force of connection, tension.
Tension, denoted by a capital T, and the Latin root of the word literally means to stretch thin. When you pull on a rope, a chain, or a string, you are applying tension.
The classic physics example from the sources is a heavy bucket hanging from a rope over a pulley. The gravitational weight of the bucket pulls down trying to stretch the rope, but the rope pulls back up, resisting that stretch.
Yeah.
The force is transmitted straight up the line.
But just like our friction example, mechanical tension has a biological counterpart that is executing the exact same physics under your skin right now.
Oh, tendons,
Hmm.
the biological cables.
Yes. The slides show a diagram of a bicep muscle connecting to the forearm bone. When a muscle contracts, it doesn't push. Muscles can only pull. They generate a pulling force that is transmitted straight through the tendon, which is basically just a high tensile biological rope directly to the bone.
It's the exact same mechanism as the bucket and the pulley.
Hmm.
The force is generated in one place and transmitted through the tension of the connective material to move an object somewhere else.
Which brings us to a really critical junction in this analysis.
Right, because we've talked about a lot of distinct forces here. We have weight pulling down, we have normal force pushing up from the ground, we have static and kinetic friction grinding against motion, we have tension transmitting pulls through ropes and tendons. We treat these as totally separate variables in our equations for students, right?
Yeah, they have different letters, different coefficients.
But I have to ask you, are these really all different physical forces?
Mhm.
Or is there a simpler way for students to view the universe?
Well, if we connect this to the bigger picture, the final slide in this deck delivers a grand synthesis that, frankly, fundamentally rewrites how you experience reality. It breaks down the difference between macro forces and their micro origins.
So the macro forces are what we just talked about, the things we experience and interact with every day.
But if you zoom into the quantum level, you realize that none of those macro forces actually exist on their own. Weight is straightforward. Its micro origin is simply gravity, the fundamental attraction between masses.
Okay, I get that. But what about the table pushing up on the block? What about the rubber tires gripping the concrete or the tendon pulling on the bone?
Normal force, friction, tension, they all originate from the exact same fundamental mechanism, the electromagnetic force.
Okay, this is the ultimate punchline of the deep dive, and I want to make sure you, the listener, are really visualizing this. When you push a heavy desk across a room, or slide on ice, or hang from a rope, you aren't experiencing three different forces. You aren't fighting some abstract concept called friction.
No, you are fighting the electromagnetic force. You are actually experiencing the cohesive bonds between atoms and molecules violently fighting to maintain their structure against deformation.
That is incredible.
Every material is just a lattice of atoms held together by electromagnetic bonds. When you hang from a rope, the tension you feel is literally millions of molecular bonds acting like tiny springs, stretching out but electromagnetically snapping back toward each other, refusing to be pulled apart.
And when you rest your hand on the wall doesn't push back because it has some inherent normal force. It pushes back because the electron clouds orbiting the atoms in the wall are violently repelling the electron clouds orbiting the atoms in your hand.
Exactly. We slap labels like normal force and tension on them to make everyday engineering equations solvable. But at the bedrock of reality, all you are ever experiencing is electromagnetism and gravity.
It really strips away all the complexity. We started with dense textbook definitions of Newton's laws and forces. We mapped them to the runway of an airplane, lawnmowers, and the biological marvel of our own joints. And we've distilled reality down to just gravity and electromagnetism.
Which is the true structural blueprint we set out to find. I really think this is the best way for a student, or really anyone, to look at physics, not as abstract math, but as the invisible rules governing everything we touch.
I couldn't agree more.
And since we've stripped everyday life down to those microscopic electromagnetic origins, I want to leave you with one final thought to ponder.
The floor is yours.
If normal force, friction, and tension are all ultimately just the electromagnetic repulsion between atoms preventing deformation, well, it means the atoms of your hand and the atoms of the coffee cup you're holding never actually touch.
Wait, they never touch.
Never. The negatively charged electrons on the outside of your atoms repel the electrons of the object you are reaching for long before physical contact is ever made.
They act like two magnets just pushing against each other.
Exactly. What your brain perceives as physical contact, the feeling of holding a solid object, the texture of a keyboard, the warmth of a mug is entirely an illusion. It is just the sensation of microscopic magnetic force fields pushing back against your nervous system. You have never actually touched anything in your entire life. How does that change the way you interact with the physical world today?